Hi, welcome to my information technology course. This is the first class in that course, which is computer hardware, and this is the first lecture in that class. So let's get started. So the first thing we need to understand computers is how binary systems work. Now, binary systems are very new. They were invented in the last century, and so it's something new that we have to wrap our minds around. Except it's not, because binary systems have been around for thousands of years. The earliest reference to a binary system I can find is the telegraph, which was invented by the ancient Romans. Now, I'm not talking about the electric telegraph, which was not invented by Samuel Morse, but a system of signaling using flags. Basically what they had were racks of flags. So I will make a crude drawing here. There's one rack. Here is another rack. So these are just basically wooden racks with, they put 5 flags. These would be flaming torches at night. And each rack would have 5 flags on poles that could be either raised or lowered, up or down, 2 states. That's a binary system. So each one of these flags on each of these poles took a couple of people to operate this. And what they could do is raise numbers of flags on these poles to signify information. And with 5 flags on each rack, they could have 1 through 5 flags raised. So in that case, it's not really binary, but we'll give them a pass at this point. And they had a cheat sheet, or a decoding paper, if you will, that had 5 columns and 5 rows. I guess I should be using Roman numerals since this was a Roman system. And this could give us 25 different possibilities. Well, that's only one short of our modern alphabet. And we could use this with the modern alphabet with a slight modification, throwing out a redundant letter or something like that. And so let's say they wanted to, well, let's figure this out. Let's say they raised 4 flags there, 4 flags up, 1 flag down. And here we'll have 3 flags up and 2 flags down. And here's a video of a replica of this system that I found on the History Channel. I hope they don't mind me stealing a few seconds of their show. And so we have 4 up and 3 up. So let's go over by 4 and down 3. That'll be right there. So we'll go A, B, C, D, E, F, G, H, I, J, K, L, M, N. That would be the letter N in our modern alphabet. And you could do everything A through Z. If we throw out 1 letter, we can do the entire alphabet, and we could easily do something with that. And so these could be seen from miles if they were big enough. People with good sharp eyes from one hill to the next could be signaling, and one person signaling on one end, another person reading at the other end. I imagine this probably took just a few seconds per letter, so we have a baud rate, if you will. I'll talk about those way down the road. Baud rate of maybe 0.3 or something like that. 3 seconds per character, and you could send messages from one hill to the other. Or you could have 1 hill here and 1 hill here, and on the second hill you have one person reading the characters and another pair of people, or however many it took to operate the racks, repeating what the first one said. And so in a matter of seconds, you could get maybe 1 or 2 seconds, you could get flags up, get a letter, get the other flags up, and relay to the next one, to the next one, to the next one. You could probably get a message all the way from France to Rome in a matter of hours. So long-distance, high-speed telecommunication is not that new. It was invented in ancient Rome, and they could actually send alphabetical messages using this system. Once again, flags in the daytime and flaming torches at night. Now, what's remarkable about this, even though I can argue that it's a binary system, flag up or flag down, but we're counting the number of flags, so maybe it's not a binary system, but it's so similar to how we encode letters of the alphabet today that it must be considered almost the same thing. Let me show you what I'm talking about. Let's erase this. We're going to just modify it a little bit. We're going to have our 2 racks. There's rack number 1, rack number 2, and this time we're going to have 4 flags. 1, 2, 3, 4. 1, 2, 3, 4. And now instead of raising a certain number of flags, we're going to raise and lower particular flags. So over here, let's raise the second flag, but have the first, the third, and the fourth down. And so it's kind of hard to see in this illustration, so I'll just draw some dots and lines. Down, up, down, down. And over here we will have all of them down. 1, 2, 3, except the last one, up. And we're going to assume that somebody can actually see this well enough. So the second rack we're going to have down, 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 up. So today we have a way of encoding the alphabet using exactly this encoding. I'm avoiding talking about ones and zeros at this point because I don't want to get into that. That can be confusing if we talk about it too soon. But if I get rid of the racks here just to show the schematic view, we have down, up, down, 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 up, and we're going to have a cheat sheet that has our possibilities across the top, and we're going to say, oh, down, up, down, down, and then down, 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 up. Oh, that's the capital letter A. And in our modern computers, we use exactly the same thing of two entities, one state, opposite state, one state, one state, one state, one state, one state, opposite state. That could be, 5 volts and 0 volts. So 0, 5, 0, 0, 0, 0, 0, 5. Or in the case of what's called RS-232, that's going to be plus 12 volts and minus 12 volts. So that's going to be minus, plus, minus, 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 plus. Either way, we have one way, the other way, one way, one way, one way, one way, one way, the other way. And if we do that, that's the letter A. And if we do this, down, up, down, 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 up, down, that's going to be the letter B. So there's A and there's B. And if we raise this one right here, down, up, up, down, that signifies lowercase letters. And so using that, we have 256 possible combinations of up and down to encode the alphabet, or voltages, 5 volts and 0 volts, or plus 12 or minus 12, or magnetized this way as opposed to magnetized that way, of the two possible entities of different things, switch closed, switch open. Two possibilities, but one possibility, other, 1, 1, 1, 1, 1, other, is A. 1, other, 1, 1, 1, other 1 is B. And we can do the entire alphabet plus punctuation, symbols, numerals, and even control codes to say to the computer to do something different. And we still have like half of them left over that we can encode other information with. So that system of racks and flags that the Romans used was very, very close to what we call the ASCII code. That stands for the American Standard Code for Information Interchange, which was developed in the United States in the 1960s. Today we have Unicode, which is a 16-place code. This is an 8-place code, obviously. We've done a 16-place we call Unicode, but guess what? Unicode is based on ASCII. If the first 8 are all zeros, then the rest does ASCII code. But with Unicode, we have 16 possibilities. That's 65,536 possibilities. So we can encode all sorts of different characters from all sorts of languages with the Unicode. But it all started with ASCII, and this Roman system was so similar that it has to be noted as a very, very early 2,000 year ago precursor to modern computer encoding. Now there's another thing the Romans did that's very similar to something we do with computers today. And this one they used jars with water, so I'll draw a jar, crude drawing of a jar with some water in it, and there's a cork here, so we can let the water out, and that's on a stand. And somewhere else on another hill is another identical jar, exactly the same amount of water, regardless of the fact that I can't draw it the same, with the same cork on the stand. And now they have a flag or a torch, and they want to send a message. Well, I'm not quite finished here. I need to put a little float here with a stick on it. So there's a float with a stick, and there's another identical stick with a float over here. And there's numbers on that stick. 1, 2, 3, 4, 5, 6 should be Roman numerals, I suppose, but anyway, 1, 2, 3, 4, 5, 6. So number, and a little pointer somewhere here pointing to numbers. Now this time they want to send a preset message, so they have a message book that will say what number represents what message, and the message could be any number of words. It could say, tell the emperor we had a victory, or who knows what. So it's a message they need to send. So to get to the right number, they have that torch or that flag again. The person sending the message raises the torch. That tells the other guy, oh, he's about to send a message. So he puts his hand on the cork there. The guy over here has his hand on his cork. Has the torch raised, he drops the flag and pulls the cork. And this guy sees the flag drop and pulls his cork at the same time. So now the water is coming out of these jars at the same rate. And so this stick is dropping down, down, down at the same rate. And he sees his stick drop down. So our water's down here now. And sees the pointer at message number 3. This one has also fallen the same amount. And when he gets down to the message he wants to send, he raises his flag, tells this guy, okay, look at the number. And we see that the number is 3. So now the message number is 3. He reads that, oh, okay, we have a victory, or whatever the message is. Well, that signaling is almost identical to RS-232. RS-232 can use a range of voltages, but basically it's based on plus 12 volts and minus 12 volts. And when one computer wants to send information to the next, it's sitting at minus 12 volts, and it raises that to plus 12 to say, I am ready to send a message. And so the other computer says, oh, that's like raising the flag. Oh, he's ready to send a message. And that stays up, and then that drops. When that drops, it says, okay, start your timers and start looking at my voltages at the correct times to get this message. So that's like dropping the flag or the torch, telling the guy, pull out your cork now. And let's say this goes, okay, we've got there, let's say it stays at minus 12, then it goes to plus 12, then back to minus 12, stays at minus 12 for a while, plus 12, minus 12, let's see, 0, 1, 1, 0, 0. I shouldn't be doing these ones and zeros yet, but you'll get the idea. 1, 0, 1, 2, 3, 4, 5, 6, 7, and 0. And then it stays there. Okay, so now, basically we have our two entities. I've gotten ahead of myself here. I started using ones and zeros, but it's just something that's it's hard not to do. So this is going to be one state. There's the other state, and it says there's, okay, 0, 1, 1, 0, 0, 1, 0, 0. And, well, that I'd have to look up to see exactly which code it is, but if it had done this instead, if I can squeeze that in there and change our, if it had done that, that would be a lowercase b. That's the same exact code. That's ASCII code. But signaling, raising the flag to say I'm about to send a message, dropping the flag to say start your timer now, is exactly the same as RS-232, where it raises the voltage, says I'm about to send a message, drops the voltage, says start your timer now, but instead of looking at one number on a stick, it looks at several entities, and it can get one state, the other state, 1, 1, 1, 1, other, and in this case we sent the lowercase b, and so every time it sends a letter of the alphabet, it goes through that gyration. I'm ready. Here it is. Start your timer. Okay, here I go again. Start your timer. And so that is something that is almost identical to what the ancient Romans were doing 2,000 years ago. So the point I have here is that what computers do today are nothing new. We're only doing things that have been done for hundreds and thousands of years, except we're doing it with electronics. So there's the earliest binary systems I could find, which were ways the Romans sent signals. So if you found this useful and informative, please give me a thumbs up. That really helps the channel. Subscribe and hit the gray bell when you do so you know when I've put up new videos. And if you want to learn information technology from hardware to operating systems, Linux, Windows, and programming, and many other things about information technology, you can go to Vocademy.net and start my course. It's all 100% free. And to help me put these videos online and to help keep Vocademy free, you can go to patreon.com/Vocademy and pledge your support. Big thank you to my patrons at Patreon. I could not do this without your support, and thanks to everyone for watching.